Good day, viewers. My name is Isaac Adeniran, and I want to teach you a very important topic in physics: resolution of vectors. But before I proceed, let me quickly do a quick introduction into the two different types of quantities that we have in physics. We have the scalar quantities and we have the vector quantities. What are scalar quantities? Scalar quantities are quantities that has only magnitude but without direction, while vector quantities are magnitude and direction. Examples of scalar quantities are speed, distance, and so on. Examples of vector quantities are forces, acceleration, momentum, velocity, and so on like that. These are vector quantities. So the discussion today will be based on vector quantities and how we can resolve vectors in case we have many vectors acting together on a single body. Now, resultant vector. What is a resultant vector? It is that single vector which will have the same effect in magnitude and direction as the original vectors acting together. Let me read that again. It is that single vector which will have the same effect in magnitude and direction as the original vectors acting. What are we trying to say? Let's say we have different vectors acting together on a body. For example, let's take forces as an example. You want to push a car, you need to seek the aid of other people to help you in pushing the car. Different people with different magnitude of force. Now, what are you trying to achieve? You want to push the car, but you are using the help of many people in order to push the car. This single vector that is responsible for pushing the car after the action of many people is known as the resultant vector. Another example is the one on our playing ground. You remember the tug of war? While some set of people will hold a rope at one end and other set of people will hold the rope at the other end. They are trying to pull the rope to themselves. But the set of people that are able to apply a force that is greater than the other set of people will be the one to pull the rope closer to themselves. It is actually the resultant vector that is responsible for the pull. Let us talk about different cases that we may have. Those are not the two examples I've given are not the only cases that we can have. Let's take all the cases that we can have. The first case, call it case 1. When two vectors are acting directly opposite each other. That is, let's say we have a vector, vector v1, and we have another vector, vector v2, acting directly opposite to each other. How do we compute the resultant vector in this place? All we just have to do is the resultant vector, which I will denote with RV, is equal to the magnitude of v2 minus the magnitude of v1, provided that the magnitude of v2 is greater than or equal to the magnitude of v1. And if the magnitude of v2 is equal to the magnitude of v1, that implies that the resultant vector will be equal to 0. Also note, for this case, case 1, the RV, the resultant vector, will be in the direction of v2. Why? Because v2 has greater magnitude than v1. For example, like in the case of the tug of war that I described the other time, the people that apply the greater force will be the one to pull the other set of people because they apply a greater force than the other set of people. Let's take an example. Two forces of magnitudes 50 Newton and 85 Newton respectively are acting directly opposite each other. Find the magnitude and the direction of their resultant force. This is a very simple example. It is just like the case 1 that we just discussed. Let's take a view at what we discussed in case 1. Say if we have vectors v1 and v2 acting directly opposite each other, the resultant force will just be the magnitude of v2 minus the magnitude of v1. Now in this case, we can say let v1 equals 50 Newton. That's the magnitude of v1. And V2 equals 85 Newton. Now, you see that the action of V1, which is 50 Newton, can be in this way, and the action of V2, which is 85 Newton, can be in this way. Then the resultant vector will just be 85 Newton minus 50 Newton, which will simply give us 35 Newton. This will be the resultant force. That is, the action of 50 Newton and 85 Newton directly opposite each other will be as if 35 Newton force is acting. But now, another thing we need to do is to find the direction in which this 35 Newton is going to act. It is obvious, but then 50 Newton, 85 Newton, which one is greater? 85 Newton is greater. Definitely, 85 Newton is going to pull 50 Newton towards itself, but the action is just going to be 35 Newton in the direction of 85 Newton. Now, this perfectly describes the magnitude and the direction of the resultant force of the action of 50 Newton and 85 Newton. Now, let's take another case. Case 2. When two vectors are acting in the same direction, this vector V1 and V2, they're acting in the same direction. For example, I talked about the case of pushing a car the other time. To have an effective push of the car, everybody pushing the car must be acting, that is, they must be pushing in the same direction. So, the resultant vector RV for the case of vectors acting in the same direction will simply be the magnitude of V1 plus the magnitude of V2. Remember from the example we treated earlier, we say we have two forces, 50 Newton and 85 Newton. But in the previous example, we say they were acting in opposite direction. But now, let us assume they are acting in the same direction. What will be their magnitude? What will be the magnitude of their resultant force? The magnitude of their resultant force, RV, will simply be 50 Newton plus 85 Newton, which will be 135 Newton. But in which direction will it act? It will act in the same direction that both of them are acting. This, as V1 and V2 are acting in this direction, the 50 Newton and 85 Newton acting in the same direction, their resultant vector also, which is 135 Newton, will also act in the same direction as V1 and V2. That is 50 Newton and 85 Newton. So let's talk about another case, case 3. When two vectors are acting perpendicular to each other, that is, they are acting at angle 90 degrees to each other. Now, look at vector V1 and vector V2. Of course, with this sign, they are acting perpendicular to each other, that is, at an angle 90 degrees to each other. Now, the resultant vector of vector V1 and V2 will definitely act in between V1 and V2, simply because V1 is acting this way and V2 is also acting this way. So their resultant vector can only act in between the two of them, which is this RV. Let me represent vector V1 with a parallel vector, which is also going to be the same in magnitude with V1, with this dotted line here, and also representing vector V2 with a parallel vector 2 of the same magnitude, which is V2 here. When I'm doing this, you get to know it very soon. Now, also, the angle theta here is showing the direction of the resultant vector from V2. I'll still talk about this direction too very soon. Now, if you look at this very well, considering the fact that the magnitude of V1 here is the same thing as the magnitude of V1 here, and the magnitude of V2 here is the same thing as the magnitude of V2 here, then I can pick any V1 that I like, and I can pick any V2 that I like. So choosing this as my V1 and choosing this as my V2, you discover that this resultant vector with this V2 and this V1, they form a right-angled triangle, which I would like to represent here. This is the resultant vector. This is vector v2 and this is vector v1. Of course, they are acting at angle 90 degrees to each other. And don't forget the theta that we talked about the other time, which is the direction. Now, from a right-angled triangle, we can make use of Pythagoras theorem to find the hypotenuse side, which is the resultant vector RV. And how do we do that? The magnitude of the resultant vector RV is simply the square root of magnitude of v1 square plus the magnitude of v2 square. That's using Pythagorean theorem. Now, the direction of RV, which is denoted with theta, is simply the arctan, that is the tan inverse of the magnitude of v1 over the magnitude of v2. But the direction of RV that I've given is biased. What do I mean by being biased? Because this direction is if I'm considering v2 as my frame of reference, that is where I'll be taking the angle from. If I want to get the direction of the resultant vector RV from vector v1, I can also use this formula. All I just need to do is to make the magnitude of v2 the numerator and the magnitude of v1 the denominator. Then I will get the direction of the resultant vector from vector v1. Let's take an example. Find the magnitude and direction of the resultant force of two forces, 40 Newton and 30 Newton, which are acting perpendicularly to each other. What do we do in this case? It is said that the forces, 40 Newton and 30 Newton, are acting perpendicular to each other. Now, let us sketch that. Since it has been said that 40 Newton and 30 Newton are acting perpendicular to each other, then this implies that we can have the 40 Newton acting this way and the 30 Newton acting this way and the perpendicularity side. Then from what we have discussed earlier, their resultant will be acting like an hypotenuse to both the 40 Newton and the 30 Newton. So this is the resultant vector. Also, the direction theta, which is from 30 Newton, can be represented this way. Now, let's compute the resultant vector first. The magnitude of the resultant vector will definitely be the square root of 30 squared plus 40 squared, which will be the square root of 900 plus 1600, which is the square root of 2500, and that will be 50 Newton. So the magnitude of the resultant force is 50 Newton. Now, let us compute the direction of the resultant force. Theta, which will be equal to the arctan of 40 over 30. And if you press this on your calculator, this will give you 53.13 degrees. So which means that our resultant force is 50 Newton in magnitude and it is 53.13 degrees from the force 30 Newton. So by this we have computed the magnitude of the resultant of the forces 40 Newton and 30 Newton acting perpendicularly to each other, and this is the direction from the small angle, which is the 30 Newton. Now let's go back case 4. Case 4 is when V1 and V2 are acting at an angle theta, which is less than 90 degrees to each other. Now, I would like us to go together with the process. Now, since V1 and V2 are acting at angle theta to each other, let us sketch it out. We have V1 and let this be V2. Of course, acting at angle theta to each other. Now, the resultant vector, definitely, it will be acting between vector V1 and vector V2. But before I do that, let me introduce parallel vectors as I've introduced in the previous case, case 3. Now, let me introduce a parallel vector which is parallel to V1. You know how we do it. V1 and the parallel vector I want to introduce, we have the same magnitude. Now let this be the parallel vector to V1. And also introducing a parallel vector which will be the same in magnitude with V2 as well. Let it be here. Then we are sure that the resultant vector of V1 and V2, definitely since this is also a parallel vector to V2, this will also be V2. Now, to sketch the resultant vector, it will be acting directly in between V1 and V2. Then I can have my resultant vector to be this. Now, what of the case of the direction of the resultant vector, either from V1 or from V2? There's nothing for us to be so sure that this resultant vector directly cuts V1 and V2. That is the magnitude of the angle between V1 and V2. The resultant vector does not cut it into two equal halves. Then we cannot be certain of the magnitude of the angle between resultant vector and V2. Likewise, we cannot be certain of the magnitude of the angle between the resultant vector and V1. But there's a way to go about that. If I extend V2, the line of action of vector V2, coming from the fact that this line of action of V1 here and the line of action of V1 here, they are parallel to each other, then the angle theta that V1 is making with V2 will also be the same angle theta that this V1 is making with V2 here. This is by the fact of corresponding angle. Angle theta here will correspond to angle theta here. Now, since this is a straight line and the total angle on a straight line is 180 degrees, then that implies that if this place is theta, then the angle here will be 180 degrees minus theta. Now, from what we did in case 3, I can extract another triangle from this as well, which will be the triangle that is involving this resultant vector here, the vector V1 here, and the vector V2 here. Now, I will have something of this nature. This is V2 and this is V1, while this is my resultant vector. Then the angle here is 180 degrees minus theta. Now, the value of the magnitude of V1 will be known, and the value of the magnitude of V1 will be known as well. Now, to compute the magnitude of the resultant vector, we make use of this common formula that we know in mathematics, which is known as the cosine rule. And using the cosine rule, we will have our resultant vector, the square of our resultant vector will definitely be the magnitude of V1 squared plus the magnitude of V2 squared minus 2 multiplied by the magnitude of V1 multiplied by the magnitude of V2, then multiplied by the cos of 180 degree minus theta. By the use of this formula, we can get the magnitude of our resultant vector. Of course, since we have a square here, that means that at the end of computing this, we need to find the square root of this. That is, finally, our resultant vector in magnitude will be the square root of the magnitude of V1 squared plus the magnitude of V2 squared minus 2 multiplied by V1 multiplied by V2, then cos 180 degree minus theta. Now, let's take an example Find the magnitude of the resultant of forces 30 Newton and 40 Newton acting at angle 60 degrees to each other. Now, since 30 Newton and 40 Newton are acting at angle 60 degrees to each other, then I can have this as my 30 Newton. I can also have this as my 40 Newton. Just like we've illustrated earlier, the angle between them is 60 degrees. Now I can draw a parallel line which is also going to be 30 Newton. Then another parallel force here which is parallel to 40 Newton. It is also going to be 40 Newton in magnitude. Then the resultant vector of 30 Newton and 40 Newton, which is this, acting in this direction. Just like we did the other time, if I extend this 40 Newton, the corresponding angle here, which is 60 degrees, so the magnitude of the angle here too will be 60 degrees. Definitely, the angle here will be 180 minus 60 degrees, which is 120 degrees. Now, if I bring this triangle out, which will be the resultant vector is here, we have 30 Newton here and we have 40 Newton here, and the angle here is 120 degrees. Now, using cosine rule, the square of the resultant vector will be 30 squared plus 40 squared minus 2 multiplied by 30 multiplied by 40, then multiplied by cos 120 degrees. Now this will be equal to 900 plus 1600 minus 2 multiplied by 30 multiplied by 40. That will be 2400. If you press that on your calculator, then cos 120 degrees will give minus 0.5. Then this will be equal to the 900 plus 1600, that's 2500 minus 2400 multiplied by minus 0.5. That will give minus 1200. Then here we have 2500 plus 1200. Okay. Now permit me to move here. Continue from here, we have RV squared will be 3700 and RV will be the square root of 3700. If you press this on your calculator, you get RV to be equal to 60.83 Newton. And this gives the magnitude of the resultant force of forces 30 Newton and 40 Newton, which are acting at an angle 60 degrees to each other. Now, having gotten the magnitude of the resultant force, which is 60.83 Newton, let's talk about the direction of the resultant force. Now, I'll be taking the direction of the resultant force from the 40 Newton force. Now, definitely the direction will be here. Let me denote it with angle phi. Now, I know the magnitude of the resultant vector and I know the angle that is facing the resultant vector. I know the magnitude of this side and I know I'm looking for the angle that is facing it. To get the value of this angle here, I can make use of sine rule. Now, permit me to use this side of the board. So remember from sine rule, using sine rule. This implies that the resultant force over the sine of the angle will be equal to 30 Newton over sine of phi. Now, the magnitude of the resultant vector is 60.83. 60.83 over sine 120 degrees, which is equal to 30 over sine phi. If you compute this very well, you find out that the magnitude of phi, value of phi, is 25.28 degrees. That is the direction of the resultant vector from the force 40 Newton is 25.28 degrees. I believe by watching this video, you've been able to understand the 4 cases as we have discussed in this tutorial video, and I hope that when you're solving question, you'll be able to use your knowledge of the 4 cases to treat questions correctly. In case of any challenges, you can drop your questions in the comment section. Thank you for watching. Also, there's a special case that I'm here to discuss, which I'll be discussing in the part 2 of this video. Before then, don't forget to subscribe. Thank you.